Throughout the United States, the superhighways designed to speed us along are actually slowing us down. They're falling apart, punished by brutal weather.
We're in Chicago. We get snow, it gets cold, it gets 20 degrees, it gets 0 degrees.
And crushed by the relentless stress of heavy loads.
One truck does the damage of 10,000 cars.
Luckily, help is on the way. Engineers and construction crews are racing to deploy new tools and new technologies to stem the tide of destruction and keep the wheels of the nation rolling on America's super roads. It's one of the largest engineering projects in the world, America's interstate highway system. 47,000 miles of superhighways, bridges, tunnels, and roads. For over 50 years, these arteries have been a symbol of American ingenuity and progress. But now, a growing population and an expanding economy have stretched the system to the breaking point. But it's not just a congestion problem. These seemingly indestructible superroads are actually falling apart. Under insidious forces of wear and tear, caused by freezing and thawing of moisture, can crack open a road from below. And also from above, the massive truckloads that relentlessly pound the roads into submission. Rough roads aren't usually life-threatening, but bridge failures can be. Our aging infrastructure is increasingly vulnerable, and we've already begun to pay a heavy price. Against the backdrop of accidents like this, cities and states around the country are scrambling to improve and expand our overburdened roadways. I'm Kevin Moore. Armed with my expertise in materials science, I'm hitting the road to see what's being done to fix America's interstate highways.
Here you go. Ah, look at that.
Right now, engineers and construction crews are working to build new highways and to come to the rescue of those we already depend on. Nowhere is the intensity of that effort more evident than along this route, Interstate 35. First opened in 1958, it is also known as the NAFTA Corridor, named for the North American Free Trade Agreement between Mexico, the US, and Canada. Because it runs right through the middle of the country, America's heartland, I-35 has become one of the busiest commercial routes in the nation. Every day, about 14,000 tractor-trailers cross from Mexico into Laredo, Texas, adding to the immense strain of traffic throughout the entire system. We'll visit 5 of the system's most critical road construction projects. From St. Paul, Minnesota, where extreme temperatures can shatter pavement like glass, through Chicago, Illinois, a hub of interchange jungles, and onto Austin and Laredo, Texas, where asphalt melting heat and big rig traffic tear up the roads. At each stop, we'll get a first-hand look at the men, methods, and machines that build America's safest roads. We start here, on the northern outskirts of St. Paul, Minnesota, where engineers are trying to solve a decades-old problem, a dangerous interchange.
120,000 vehicles come through here each day, and because it's laid out poorly, there's accidents, people cutting across lanes, traffic, all sorts of problems. But right now, the Minnesota Department of Transportation is working to make it a well-oiled machine.
In the first 19 years of operation, the I-694-I-35 East interchange was the scene of over 1,800 accidents. This, and at least 24 other interchanges around the country, all share a common problem. They weren't designed to accommodate today's traffic volumes. This exchange combines 2 roads using an X-shaped merge pattern. As traffic flows into the interchange, all vehicles from both highways are forced to converge onto a 3-lane common section. Once in this automotive mixing bowl, drivers must quickly choose which highway to depart on. The problem is that some drivers need to careen across all 3 lanes in just 1 short mile in order to make their exit. The result is a classic traffic nightmare. To correct this dysfunctional layout, engineers have redesigned the entire interchange. In the new design, motorists will be able to choose their route before entering the dreaded common zone. The first step in unweaving this weave is to demolish roughly 3.5 miles of highway by first rerouting traffic.
The legislature mandated that we keep traffic moving through here, that we do not bypass it, we do not shut anything down.
With traffic rerouted onto nearby lanes, a pair of excavators begins ripping apart and removing the old asphalt road. But right now, work is halted because of an equipment problem. The teeth on this excavator's bucket are wearing out, and it's mechanic Jason Walraff's job to fix the breakdown pronto.
So how does this happen? Why is this all worn down?
A lot of friction, a lot of heat.
These abrasion-resistant, hardened steel alloy teeth are designed to last for 300 hours of use. But here they're only lasting about 60 to 80 hours because of the extreme friction caused by scraping against the hard asphalt and the layer of concrete below.
As you can see, the shank is sticking out of the tooth. That's something you want to correct before that happens by replacing with a new teeth.
So basically, this is actually part of the bucket. This is the piece that's replaced, and so when you wear that down, you're wearing down the entire bucket.
Yep.
All right, let's knock it off. This is actually one that's been worn down too far.
Yes.
And it started to wear on this piece here. That's actually the piece of the bucket.
Yep, you can see just a little bit of wear right there. That's something we want to stop.
Friction-heated tar has seeped into the removable teeth, causing them to stick to the bucket.
There you go. Got her.
Now, we can put the replacement teeth onto the bucket.
And these are the nice new ones. This is what they should look like from the very beginning.
There is a little cleanup process. I get all that tar and dirt out of there. All the tar is in there from scraping all this asphalt.
And so I take it you just twist it on?
That's correct.
All right, so Jason, is there a special way these go in?
Yep, they're pretty self-explanatory there. They can only go in there one way.
All right, wait.
So you just hammer it down
and so I just whack it?
Just whack her away and try it. You got it. As easy as that.
Now the team can get back to removing all that asphalt. The operation begins with another excavator, fitted with a special gouging hook, which rips through the 4-inch thick pavement like a knife through butter. Next, the newly refitted bucket excavator comes along and loads the loose asphalt chunks, weighing up to 300 pounds each, into a dump truck. The dump truck then piles the debris onto a growing mountain of asphalt near the demolition site. Later, this material will be recycled as an aggregate base layer under the new pavement. Down the road, a guillotine breaks up an 8 to 10-inch thick layer of steel reinforced concrete. This earth-shaking road breaker is run by Dennis Bishop.
And why a breaker and not a jackhammer?
Well, the jackhammer would be so time-consuming and so much labor. In a couple of days, I can accomplish what would take these guys a jackhammer a month.
All right.
Stand back where we can watch it, and away we go.
This 6-ton solid steel guillotine can drop from varying heights depending on the thickness of the road being broken, unleashing up to 84,000 foot-pounds of force. It's an ingenious solution that takes just one operator. Well, actually, there's really not much operating to do.
So I noticed that no one's in the cab. You control all of it out here with remote operation.
You can steer everything. It's an emergency stop setup. You can catch the hammer, like if something's about to happen. I mean, you can basically interrupt the operation.
A day after the guillotine finishes breaking up the concrete, an excavator with a grappler attachment separates the rebar from the concrete rubble. The steel rebar will be recycled, and the concrete will be crushed into rubble and reused as stone aggregate in a new concrete road. But rebuilding a road doesn't always require complete demolition. A road can be resurfaced like a house can be repainted. 400 miles away in Chicago, Illinois, a more surgical style of demolition is underway at the Dan Ryan Expressway Bridge. A 2.5-mile stretch of elevated highway crosses over a commuter railroad and the city's Armour Square community. The road surface on this bridge is showing signs of wear.
Just like when somebody gets older, you get that first wrinkle, you know, that first gray hair, we started getting some potholes, some cracking. So we knew that we're going to have to do something eventually.
Since other sections of the Dan Ryan Expressway are under construction, the state of Illinois decided to also fix the bridge, extending its life another 20 to 30 years by resurfacing the elevated roadway. Step 1. Precisely remove a 1/4-inch layer of the old concrete surface using a cold milling planer. It takes 2 days to grind just 2 lanes of highway, which is fast compared to the speed of the next step. To remove another 1/4 inch of concrete, these 2 trucks perform a special task called hydroscarification. The operation begins inside this lawnmower-sized housing. A spinning blade sprays 16 gallons of water per minute at 34,000 pounds per square inch of pressure. All the concrete aggregate removed by the sprayer is vacuumed through this hose into the lead truck. So all that remains is a clean but jagged surface.
When we pour our concrete on top of that, it binds it very well.
Resurfacing the elevated road has proven far less invasive than replacing the entire structure from the ground up. But this minor surgery can't stave off the inevitable, because eventually this bridge, like all bridges, will have to be replaced. Coming up next, the nation's focus shifts from crumbling roads to aging bridges. Then, see how workers erect a new span in Illinois. One of the largest engineering projects in the world, America's interstate highway system. 47,000 miles of highways, bridges, and interchanges has been pushed to the breaking point. Now, builders are in a race against time to add capacity by building new roads and bridges, and hopefully alleviate traffic jams never imagined when the interstate system was designed. On June 29, 1956, President Dwight D. Eisenhower signed a law creating the Interstate Highway System, a national network of roads to help Americans travel faster. A huge improvement over the nation's haphazard network of country roads, Eisenhower's vision was inspired by Germany's 4-lane Autobahn, used by American soldiers to pursue Hitler's army at the end of World War II. During the Cold War, such highways could help the United States meet the demands of strategic defense or national crisis. Over its 50-year history, the interstate system has helped give birth to the first modern suburbs, long family road trips, and highway traffic jams. As traffic increases, some of these hackneyed highways are becoming roads to ruin. And perhaps the greatest problem facing motorists is a bridge collapse. That peril became all too evident just 11 miles to the southwest of our construction project in Minnesota. It was here, on August 1st, 2007, that a bridge on Interstate 35 West gave way without warning, dropping about 100 vehicles 115 feet into the Mississippi River. Nearly 100 people were injured. 13 perished. and forensic engineers immediately began the painstaking work of finding the cause. Meanwhile, the Minneapolis collapse has focused attention on almost 100 other aging interstate highway bridges in the United States. It has also raised the stakes for engineers to design new structures that face increasing traffic loads. A few hundred miles to the south, in the suburbs of Chicago, engineers are dealing with a much larger kink in the interstate highway system. Here, at the construction site of the Des Plaines River Valley Bridge.
It's a very large structure, 1.3 miles long. It will carry 6 lanes of traffic, 3 lanes in each direction. It will be the second longest bridge in the state of Illinois.
This bridge is the linchpin of a 12.5-mile extension of Interstate 355 that will connect to Interstate 80. But the extension passes right through the habitat of an endangered species, the Heinz emerald dragonfly. Protecting this species' delicate environment presented engineers with a major challenge: how to build a bridge that doesn't interfere with the wildlife or the integrity of the wetlands itself. Their ingenious solution involved 2 critical design adjustments in order to make the bridge environmentally friendly. The bridge height was raised to 100 feet so that the structure won't impede the dragonflies, which can fly as high as 80 feet off the ground. Designers also increased the distance between the supporting piers to reduce the number of footings placed in the sensitive wetlands. The increased elevation may be great for the dragonfly, but for the construction crew, building a bridge this high means undertaking dangerous hoists.
The purpose of the safety meetings are because even though you're one train...
There's no such thing as a minor accident when you're picking 132 tons of concrete girder, so safety is always the highest priority on the construction site.
If you see something that's not right, you say something to stop it. You need to be aware of what ironwork...
The bridge is now 4 months from completion. Workers are gearing up to lift the 558th of 612 of these precast concrete beams.
The beam segments are of such a weight, up to 265,000 pounds, that it requires a capacity of 2 relatively large cranes to lift them into place. And they're set up and rated at 275 tons and 300 tons each.
The longest beams stretch an incredible 171 feet, but that's just half the distance between piers, up to 271 feet, which means only one end of the concrete beam actually sits on a pier.
So James, the green plates they're putting the beam onto, what is that?
It's a bearing pad that the bridge sits on. It's got steel shims inside, encased it with rubber, and as temperature heats up and cools down, the bridge expands and contracts, and it gives it a place where it can move.
The operator needs a delicate touch to precisely place the beam onto the bearing pad. The other end of the beam rests on a temporary shoring tower, and it's at this end that the beam's special design comes into play. Here's what makes these extra long girders so strong. Steel cables will pass through holes cast into each beam. In order to knit the 2 beams together end to end, workers first build an internal rebar cage, connect the cable conduits, and then surround the 1-foot gap with a wooden concrete form. Then the team adds concrete to splice the 2 girders together, creating one solid piece long enough to span the distance between 2 piers.
So James, we're pouring concrete?
That's right.
And all in all, how much concrete are we going to put in there?
I think there's 30 yards. It's about 4 truckloads is what they usually bring out.
Then they come in with their hand vibrators, and they excite the concrete and get it to settle in and take out the air pockets, right?
Yeah. Inside that closed bore, you've got all the rebar. There's post-tension ducts that run through. There's a lot of obstacles of that vibrator. It moves that concrete around and gets it to all the corners and make sure you have good consolidation.
Once the concrete is hardened, workers begin the post-tensioning process, which gives the 2 girders the rigidity of a single unbroken unit. First, workers thread a series of 14 1/2-inch diameter steel cables through the empty ducts within the beams. Then they jack the cables to 600,000 pounds per square inch of tension.
The tension in the cables is transferred to the beams and holds the beam segments together to a point where they behave as one beam.
The next step is to build a road atop the bridge, a process with just as many complexities. Coming up, how interstate highways are paved with reinforced concrete. And later, we'll see just how tricky asphalt paving can be when builders halt a multi-million-dollar construction project. Along the 1,600-mile Interstate 35 corridor, one of the most heavily traveled commercial trucking routes in the country, crews are desperately working to expand roads for the expected surge in traffic in the coming years. To cope with increasing traffic loads, engineers are rethinking the most fundamental assumptions about the way they build highways. From the bottommost layer to the very surface that grips your tires. Here outside Austin, Texas, crews are building a highway called SH-130 to bypass I-35 traffic around the state capitol. Because of the tremendous wear and tear this road will have to endure due to increasing trucking, the Texas Department of Transportation has decided to spare no expense when it comes to durability.
All right, I think I'm getting it.
A construction crew installs a rebar mat that forms the backbone of continuously reinforced concrete pavement. The most durable and the most costly type of road surface, about $10 per square yard more than non-reinforced roads. The rebar helps make this $1 billion project the most expensive road in Texas history.
So now that it's all laid, what's the next step?
They'll even them all up on the end and start tying.
Tying it off, I take it I'm doing this by hand.
Exactly.
How's that
with
work?
A pair of pliers and a tie wire reel.
Each of the estimated 8 million ties is critically important.
One strand like that?
Right here?
Yeah.
In the middle.
Tying not only maintains the structural matrix during the concrete pour, but it also helps the concrete maintain lateral rigidity when the pavement cracks.
Now shoot for 27 a minute.
Let's not get ahead of ourselves. I'm happy I just did 3.
You'll get it.
So once this is all tied up, the next step is the concrete gets poured on, right?
Correct.
Finally, we're ready for the concrete, which is being mixed in a mobile plant built for the construction of this highway.
These concrete stations are fascinating and mobile. If you look, you'll see there's wheels on them, and this is so they can move them to wherever they're pouring concrete.
The plant is also computer controlled to properly measure the right amount of materials that go in the mix.
Now, what I can do from there, I can actually send a message to the plant to go ahead and start batching that order for me. I'm gonna go ahead and turn on my belt manually.
Uh-huh. And so everything's gonna go up the belt into the mixer.
Concrete is a composite material made out of 4 basic ingredients: stone, called aggregate, sand, Portland cement, which serves as the chemical binder for all the materials, and water. The plant's drum mixes all the ingredients together to the right consistency. After the mix is finished, the concrete is transported by dump truck to a paving site. But in today's case, this concrete is destined to become a massive bridge column, which means it goes into a mixer truck and then must be cooled. Cooling is a huge concern in bridge columns because such a thick mass of concrete tends to harden unevenly and can crack if the temperature is above 85 degrees Fahrenheit. Scientists have developed a cooling method that doesn't add water or otherwise change the chemistry of the mix.
What we do is shoot them with liquid nitrogen.
Really?
Yes.
Liquid nitrogen?
Yes.
This 11,700-gallon tank contains liquid nitrogen, a cryogenic fluid.
We'll go ahead and shoot it for about a minute with liquid nitrogen. It's going to drop the temperature rapidly.
When the crew releases the liquid nitrogen, it vaporizes and shoots through this retractable injector wand.
Wow, look at that.
Liquid nitrogen in its gas form.
The temperature of the liquid nitrogen is 320 degrees below zero. After a 1-minute blast, the gas cools the concrete slurry down to 75 degrees Fahrenheit.
It goes in as liquid nitrogen, but then it becomes a gas, and because it's not further wetting the concrete, it doesn't dilute its strength.
Exactly.
All right.
The concrete stays cool for about an hour, plenty of time to deliver it to the bridge pour site. Early the next morning at another Highway 130 construction site, crews are building a 1-mile lane of concrete road. Once these paving machines begin making road, they should not stop, because this extremely dry mix of concrete could harden too much if it doesn't pass through the final machine in time. Paving Superintendent Jerry Sanders makes sure the entire process runs smoothly.
Why is it not wet?
In a slip-form paving operation, because there's nothing to hold up the outside edges, you have to pave it dry so that it will stay put and it will stand up after the paver goes across it.
The paving process begins when a dump truck feeds its 10 cubic yard load of concrete onto the paver's 1,600-pound retractable conveyor. The deluge of material forms a large pile in front of this first machine called the spreader. Using huge augers, the spreader distributes the concrete evenly, both in thickness and in width. Following the spreader is the finishing machine. It too has large augers that knead the concrete to keep it from hardening. Amid the augers are 18 vibratory probes which shake out any air pockets in the concrete. As the finisher moves forward, it pushes the concrete into a constricted space of stainless steel slip forms. One form slides against the concrete on the road shoulder. The other pushes the top of the concrete flat to produce the road surface. To ensure the forms stay at a consistent 12-foot width and 14-inch depth, the paving machine has 2 sensors that ride along a guide wire placed on the side of the open grade by surveyors. The new road surface is taking shape, but the concrete must be finished manually, a creative job I could probably handle.
It's a 20-foot magnesium straight edge. We use that 20-foot straight edge to check the ride of the concrete, to make sure that the paver is doing what it's supposed to do and not leaving any bumps or dips in the concrete as it's paving through. Keep letting the handle down so you got your square edge going across.
All right. How's that?
Now then turn the handle all the way back.
Like that?
See, it rolls the edge over and just pull it back.
Just pull it back. Simple as that. Just pull it back. So what do you think? Did I do a decent job?
I think you're hired. Right there.
Next, the builders apply a final touch using a mechanical rake. This machine creates water drainage grooves and then sprays a curing agent on top to help the surface harden. But there is a much cheaper and more common method of paving America's interstate highways. It's just not as durable or long-lasting as concrete. Coming up, discover the hot and sticky world of asphalt. And later, interstates in the age of the information superhighway. Rolling along America's interstates, most drivers experience highways paved in one of 2 different materials: concrete or asphalt. Concrete is more durable, but because of the expense, only 5% of America's interstate highways are paved with it. On average, asphalt costs $55 a yard less than concrete. Builders can pour it faster, and asphalt roads can be opened quicker. The only problem with asphalt, it wears out and must be resurfaced or replaced twice as frequently. That can mean trouble for motorists and for the builders who must dodge the elements to keep the highways open. In Texas, all along the Interstate 35 NAFTA corridor, heavy rain and flooding are impeding road building progress.
In the last 3 months, we've lost roughly 50% of our work days due to rain. And you normally would plan for some bad weather in a construction job, right? But it wouldn't be 50%, it might be 5%.
Weather delays have been a huge problem here in Laredo, Texas, where the state is trying to repave a 5.5-mile section of I-35 that's been battered by constant truck traffic. To accommodate the increasing onslaught of 18-wheelers, engineers are also widening the highway by adding a third lane on each side of the median. The $53.1 million project started 3 years ago and has been on schedule. But bad weather has caused serious problems.
Well, it looks sunny and beautiful here. In reality, it's been raining like cats and dogs, day after day. And what that means is this aggregate is too wet to make good asphalt. We can't work.
Asphalt pavement requires dry aggregate in order for the second basic ingredient, asphalt, to bind it all together.
Asphalt is basically a byproduct of petroleum refining operation. So when they take the crude oil and refine it, what's left over is liquid asphalt. And this liquid asphalt is used as a glue to hold the rocks together, and the combination of the two is what we call hot mix.
The last time this asphalt plant produced hot mix was over a month ago. The weather delay is agonizing for contractor Jim Price.
You can't make asphalt right now and you can't pave. What's that mean for your operation?
We're at pretty much a standstill. Our crews are on standby and equipment is idle, and time is money.
Jim is eager to get the show on the road. His lab tests the aggregate every day to see if it's dry enough to make hot mix.
Well, first of all, we need to see how much moisture we've got. We need to start with our raw aggregates that we use.
I take it we're going to do it with this stuff?
Yep, it's nothing more than just a microwave oven and a set of scales.
To determine the moisture level, a technician weighs a 5-pound sample. Then he dries it using a microwave oven and weighs it once more. The weight differential between the wet and dry aggregate tells him the amount of moisture in the sample.
2288 grams to begin with, and then 2255 to end with, so about 33 grams of water in there makes 8.8% moisture.
Are those numbers correct?
Unfortunately, this test result is problematic.
So we have 8.8% moisture. What does that mean to the asphalt?
It means that we have a lot of water in the mix coming out of the actual material.
So 8.8 is pretty high.
Yes, it is. Normally we wouldn't run with 8.8%, but there's something you can try to work with. At 10%, higher than 10%, you can't do anything with it.
So 8% is somewhat usable. What would be optimal?
Anything lower than 2%. 0% would be the ideal.
Jim faces a difficult decision. The state wants him to get the project back on schedule, but not at the risk of making poor quality hot mix.
When can we actually get back to work?
Well, provided we don't have any rain tonight or in the morning, we're going to fire the plant up and see if we can produce quality mix.
The night passes without a drop of rain. Jim finally orders the plant to power up for the first time in over a month. First, a front-end loader fills the aggregate bins with stone and sand. Then a conveyor transports the aggregate mixture to a rotating kiln. Fired to 2,000 degrees, this kiln process dries the aggregate a little, but not enough to reduce the moisture content to 0. Next, the machine injects hot liquid asphalt into the mixture, which tumbles some more.
By the time we get out, we'd like to have about 300 to 325 degree mixture.
Now a conveyor carries the hot mix to a hopper above the waiting truck. A trap door at the bottom opens, dropping a 25-ton load into the trailer. The driver has just under 2 hours to get the mix to the work site 7 miles away. If he takes too long, the asphalt may cool too much to be poured.
It becomes very rigid, and you lose your ability to compact it.
But chances are cooling won't be a problem. Today weather is dry and hot, over 100 degrees. Good conditions for the restart of Jim's operation.
Well, it's a lot of relief to get production back to rolling again. Unfortunately, the rain has still slowed our production down. But we plan on trying to make up some days through working weekends and double shifts.
Jim's crew is building a special type of asphalt road that's supposed to last as long as concrete. It's called perpetual pavement.
We hope to build a pavement that will perpetually last. It is the same asphalt, but it's designed in several different layers.
6 layers in this case, which add up to 15 inches of asphalt from top to bottom. Each successive layer contains varying sizes of aggregate. The lower layers, comprised of stones 1/2 to 1 inch in size, are specifically designed to be flexible and resist cracking or rutting, which always starts at the bottom. The upper, thinner layers use smaller stones to create a smooth ride for motorists.
Those layers, they have a short lifespan, so we count on going there every 7 to 10 years, removing that thin layer, putting another one down there.
Today, the second layer of perpetual pavement is being laid down. Each layer is poured using a technique very common throughout the Southwest United States. Step 1. The hot mix is poured from the belly dumper right onto the road, forming a continuous berm called a windrow. This unbroken supply of asphalt increases productivity and ensures uniformity throughout the entire process. Next, a windrow elevator machine transfers the hot mix into the paver. Rotating paddles at the elevator's mouth pick up the asphalt and send it into the paving machine's hopper. From the bottom of the hopper, a conveyor feeds the asphalt to the back of the machine, called the screed. Much like a concrete slip-form paver, the screed spreads the material around with augers. And it also vibrates to partially compact the asphalt. Behind the screed lies a fresh layer of asphalt, spread to 3 inches thick and 12 feet wide. Next, 4 rollers flatten the asphalt. Each 10 to 15 ton machine rides on 2 6-foot wide, 4.5-foot diameter drums, specifically designed to squeeze out air pockets where moisture could later collect.
The first roller is a straight vibratory roller that vibrates vertically. The next 2 rollers in line are what we call our Aussies. They not only vibrate vertically, but they also oscillate horizontally to try and basically knead and pound the mix in as tightly as possible.
The final 10-ton finishing roller bears straight down without vibration. After each roller has driven over the road 4 times, the asphalt is finally compacted to 95% average density, meaning 95% of all air has been eliminated. After the crew finishes paving this 1.5-mile stretch, they'll be back to add 5 more layers. They're scheduled to complete the entire widening project in the summer of 2008. But before any of the heavy-duty road along the 1,600-mile NAFTA corridor can open, some often overlooked additions must be built along the side. Coming up, from crash barriers to smart road technology, see how safety is built into every road. Highways throughout the United States and along the Interstate 35 NAFTA corridor are built for speed, durability, and longevity. But perhaps the most important and least visible feature designed into these megastructures is safety. And on the highways where heavy traffic roars along at 65 miles an hour or greater, safety means preventing collisions, specifically head-on collisions. That's where the concrete crash barrier comes into play. Back at the St. Paul, Minnesota interchange, this crew is building a brand new median wall. The barrier stands 7 feet tall and about 3 feet wide at the base. It can absorb a glancing blow from even an 18-wheeler. No matter what the size or function, concrete barriers are designed to be easily assembled using the slip-form barrier machine. Slowly but surely, it inches forward, automatically steering along surveyor guidelines. The building process begins when a worker empties concrete from this mixer truck onto a conveyor belt. The belt carries the material up to a hole above the slip-form machine. As the concrete fills the barrier-shaped form, vibrating probes at the end of these red lines shake out air pockets to compact the concrete mass.
They're in 7 different spots hanging in there. If you grab one of these, you can feel the vibration.
Oh, yeah.
The form slides forward, revealing a brand new barrier wall. The machine can churn out about 1,200 feet of wall in a 12-hour workday. But it's up to these masons to add a perfectly smooth finish in the wet concrete using hand trowels. It's easy to see that this crew takes pride in their work. But I can't believe their next move. The destruction of a finished wall?
Troy, why are we ripping down this freshly poured section of the wall?
This is where a light pole goes. We have to rip this out because there's a bunch of steel that goes in there.
So how big of a section do we need to rip out here? I mean,
there's 15 foot.
So this is
15 foot wide.
That's our 15-foot section.
Yep.
All right, well, can I help? Look at that.
Right ahead.
Build a wall up, I tear it down.
We're gonna let the Bobcat come and finish up here. He's gonna dig this out and go a lot faster.
So Troy, you think I can drive the Bobcat?
I think so.
You're a brave man. All right.
This will be interesting.
Out of all the machinery used in this road construction, this Bobcat is the only one an amateur like me can safely operate. But I need to be very careful not to snap the conduit embedded in the bottom of the wall that will carry electricity to a light pole.
So we've taken the wall down, Troy. Now the next step is what?
Electricians have to cut that pipe, run their conduit up, and then we just pour it back in.
After the conduit pipe is extended and mounting bolts with rebar are installed, workers build forms around the gap. Then concrete is hand poured to complete the wall and anchor the light pole's support structure. Once the concrete is hardened, workers wire the light post. Hoist it into position, and finally bolted onto the barrier wall. Unweaving the tangled mess of the I-35 East, I-694 interchange will take another 15 months. When unveiled in the fall of 2008, it will be a much safer road and traffic will flow much more smoothly. But back in Austin, Texas, there's another way to monitor and control traffic woes. 74 closed-circuit television cameras peer down at the highway along Interstate 35. The images are transmitted by fiber optic cables to the state-of-the-art Combined Transportation, Emergency, and Communication Center, or CTEC. Here, traffic control agents bear witness to a disturbing trend.
But now, with the amount of traffic that we have, with the increase in the population, every major highway is backed up and stacked up every day during rush hour, morning and afternoon.
Austin, Texas is the third fastest growing large city of the United States, and the volume of traffic traveling through Austin on I-35 has multiplied from 134,000 cars a day in 1987 to 230,000 cars in 2006. Opening bypass routes like Highway 130 can alleviate some of the congestion, but smart road technologies are fulfilling an even bigger need.
Keeping the lanes open is of paramount importance. There's lots of money, lots of man hours at stake out here.
It's about 4 in the afternoon, and the 3-hour-long peak period is just beginning. The agents monitor TV screens to identify any traffic problems.
This is a bit unusual for traffic to be backed up like this time of day. So I can turn the camera around and try and see if I can find the source of the backup, whether it's a collision, debris in the roadway.
A stalled vehicle is the culprit. Agents spread news of the problem via the internet, TV, and radio. And they can instantly alert motorists by way of 16 dynamic message signs.
10-4.
The system is also designed to solve problems by dispatching highway emergency response operators to clear the road.
They have the ability to be able to hook up with vehicles to pull them out of the roadway.
Clearing traffic jams is a never-ending battle that will only get more intense over time. And with traffic volume on America's interstates increasing in the coming years, engineers will need to continually increase capacity, rebuild and repair overtaxed roads, and implement the latest road designs and technologies. For now, the engineers at each of these construction sites along Interstate 35 feel they're staying ahead of the curve.
But all that may be wishful thinking. As populations increase, roads see more use, weather patterns become ever more extreme, and interstate design and engineering gets more advanced, highway systems of today may become tomorrow's next construction project.